Hi everyone, welcome to Data Nutshell. So far, we have seen that RAID 5 is one of the most popular RAID levels because it balances performance, reliability, and storage efficiency. But like every technology, it isn't perfect. RAID 5 comes with some serious limitations that we must understand, especially if we are designing systems for critical workloads. In this video, we'll cover three major weaknesses of RAID 5 in detail that are the write penalty, the rebuild time, and why RAID 5 struggles with write heavy workloads. So let's see what write penalty means here. Let's consider this scenario that we have five data disks and one parity disk. And in one iteration, we got data blocks D1, D2, D3, D4, D5 across those five data disks and a parity block P corresponding to those five data blocks. Now, say that you want to update one of those blocks. Say we want to update D2. What happens in this case? When updating a block, we need to keep the parity consistent. That is, if you are updating one of those five data blocks, you will have to update the parity block corresponding to those as well. But instead of recalculating parity from scratch, we use a smarter XOR trick. So let's say what's the naive way to do it? The naive way to do it is that we read the values of D1, D3, D4, D5 from those data blocks. We have the newer value of D2 and we recalculate the parity using D1 XOR new D2 XOR D3 XOR D4 XOR D5. But that means we have to read all the existing blocks from the disk, which is very expensive. What's the XOR trick here? The XOR trick says that the new parity is equal to old parity XOR old data XOR new data. Why this works? Because we know XOR is self cancelling. That is, A XOR A is 0, which means XOR of a value with itself cancels it out. So when we do old parity XOR D2, we are effectively cancelling out the effect of D2 from older parity. So new parity is old parity XOR D2 XOR new D2. That's how it works. So if we want to update just one block of data in a RAID 5 array, what's the exact sequence? The first thing is read the old data block. The second step will be read the older parity block. Third is to calculate the new parity using old data XOR old parity XOR new data. Then the fourth step is to write the new data block to the data disk. The fifth step is to write the new parity block to the parity disk. So we saw that it was a single request, but it became two read operations and two write operations. That is four output operations in total. That's why we say that RAID 5 has a write penalty. For every write, we had to do four input output operations. What's the impact of it? The impact is that small random writes become very slow compared to say RAID 0 or RAID 1, and applications like databases, logging systems, or transaction heavy workloads suffer heavily because of this. The second limitation is the rebuild time. As we know, RAID 5 can survive the failure of one disk, but rebuilding that disk is a huge challenge. So, what happens when a disk fails? Every block that was on that failed disk must be reconstructed using the parity block for that stripe and all the other data blocks in that stripe. That means all the surviving disks will be hammered with extra read activity during rebuild because we will effectively have to read all the surviving blocks to reconstruct the lost blocks. How is it a problem in large modern disks? Because, say, in the early days of RAID, disk used to be small, maybe a few GBs, and rebuilding was quick. But today we have multi terabyte drives, and rebuilding can take hours or even days. And what are the consequences during rebuild? The first is performance hit. Normal input output operation will slow down because disks are busy rebuilding. Applications will see degraded performance until the rebuild is complete. The second thing is the risk of second failure, because RAID 5 only tolerates one disk failure. If a second disk fails before the rebuild finishes, we will lose the entire data. With longer rebuild times, this risk window becomes very large. So, this is why many organizations move to RAID 6 from RAID 5, because RAID 6 can tolerate two disk failures. The third limitation is that RAID 5 is not good for write heavy workloads. So, RAID 5 works best when the workload is read heavy, that is, there are more read operations coming than write operations. But when write operations dominate, RAID 5 quickly shows its weaknesses. Why? Because as we saw, it has write penalty. Each write involves four input output operations on the disk, and the parity update process slows down the write throughput. In these cases, RAID 5 performs significantly worse than, say, RAID 10 or RAID 6. That's why enterprises avoid RAID 5 for critical write heavy systems and instead use RAID 10 and RAID 6, which we will cover in the upcoming videos. So, what is the summary of the weaknesses of RAID 5? The first is write penalty, that is, four input output operations per write, which slows down small random writes. And the second thing is it takes high rebuild time and involves risk, long rebuild times with large modern disks, and high risk of total data loss if a second disk failure occurs. The third thing is write heavy workload limitation, because RAID 5 is good with read heavy workloads, but for write intensive systems, its performance drops significantly. In short, RAID 5 must be chosen carefully. It's great for backups and read heavy workloads, but not for databases or mission critical write heavy systems. So, RAID 5 was a breakthrough design because it balanced storage efficiency, fault tolerance, and speed, but it has its weaknesses with write penalty and rebuild risk. So, if you are planning a storage system, we have to think about the workload pattern, the disk sizes, the tolerance for downtimes, and data losses, and that will tell you if RAID 5 is suitable or not. In the upcoming video, we will cover RAID 6 in detail. So to stay tuned, please press subscribe. Thank you.